Coupler curves. The coupler is the most interesting link since it has complex motion. Points on the coupler can have path motions of high degree. By degree, we mean the highest power of any term in the equation. For example, a circle is a second-degree curve. Pin-jointed 4 bars have in general a 6th-degree coupler curve. A 4-bar slider crank has in general a 4th-degree coupler curve. If the linkage is pin-jointed, as the 4-bar all-revolute is, the highest degree of its coupler curve is given by the following equation, where n equals the number of links. All linkages that have floating coupler links will generate coupler curves. For any coupler, we have an infinite number of points which trace out complex curves, all of which are different. Now, by infinite number of points, what we mean by that is that a coupler, though it is often shown as simply a straight line between one link, in this case probably called the crank, and another link called the rocker, both of which are pinned to ground. We usually think of it as a straight line between these two. However, the coupler can have any shape, and in this particular figure, we show the coupler kind of shaped like a big kind of pink blob. And any one of these points could be the coupler point, and that point would trace out a curve as the crank, or link 2 in this case, traveled around this circle. You can imagine, for example, placing a pencil right there in that hole, and then you'd see that pencil trace out a particular curve as the crank rotated. That curve that would be traced out by the pencil would be called the coupler curve. We could again put the pencil in this point and it would trace out a different path, or perhaps put the pencil here at this point and again trace out a different path. Since we have an infinite number of shapes which we can draw and an infinite number of points inside of that shape, every linkage traces out an infinite number of coupler curves. Coupler curves can be used for generating useful path motions, and it is the solution to the path generation problem. Here's a sample of 4-bar coupler curves. We have the pseudo-ellipse, we have kidney beans, we have banana-shaped coupler curves, crescents, single straights, in which case we have one straight path on the coupler, double straights, in which 2 sides of the coupler curve are pretty close to straight, teardrops, which contain a cusp or a point of 0 velocity, a scimitar, an umbrella, a triple cusp, a figure 8, which contains a chronoid or a place where the coupler path crosses over itself, and a triple loop. All of these are paths that the coupler point would follow. So if we go back to our previous discussion, this is a particular kind of weird shaped bubble coupler, and every point on this coupler traces out a particular path. Some of the paths traced out by this coupler would be shown here in this figure. The black line would represent the path of the coupler, and the pink is just shaded in just to show what the path looks like, to give it more definition. So the coupler point actually travels along this black curve. There's an infinite range of variation of curves. Features of interest on these couplers are as follows. Double points are points with 2 different tangents. We have cusp. These are sharp points, or points of instantaneously 0 velocity. And we have chronoids, or multi-loop curves. The 4-bar coupler can have up to 3 double points. If we go back to our pictures, we'll see, for example, the triple loop has 2 chronoids and 1 cusp. So it contains 3, which is the maximum of double points that we'll have. The figure 8 contains 1, just 1 chronoid. The scimitar has 2, a cusp on either end. there's a Rones and Nelson atlas of 4-bar couplers. We call it the H&N atlas. Here's a page from that atlas. That H&N atlas demonstrates curves that will be traced out for a given linkage. These different curves are generated by connecting a point on the curve to our coupler. Here's an example. Here we have a crank, a coupler, a rocker, coming back down to a second ground position. So this ground position is O2, this ground position is O4. The length of the crank is always of unit length in the H&N atlas. You can see that if you focus in here on this guide, where we have 1 representing the crank length. A, or the coupler in this case, is equal to 3 times that 1. The rocker here, represented by B, is equal to 3.5. And the ground length between these two positions, C, is 2 times. So we can scale this linkage. For example, if we wanted our crank to be equal to 2, then we'd have a coupler equal to 6 units, or 6 inches perhaps, and we'd have a rocker equal to 7, and a ground length equal to 4, just scaling everything by our crank length. Notice our crank follows this particular path, and if we want to trace out a particular coupler curve that we see here, of which I believe there will be 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 different coupler curves, we simply need to put this point here on our coupler. So if we wanted to trace out, for example, this curve, which is shaped kind of like a banana, we'd simply take our coupler, and instead of having it be just a straight line, we'd make it a triangle. So we'd come down here, touch that point, and then go back up. And then what we find is this point here, which would be contained in our triangular shaped coupler, would trace out this path as our crank rotated completely around. If you notice, there are dashes along each one of these curves, and these dashes are of different length. These dashes represent 5 degrees of crank motion, and so as the crank moves at a constant rate along this path, we find that the coupler point speeds up and then slows down as we travel along. And so what you do with the H&N atlas is you, for example, you're designing a linkage and you need it to perhaps trace out a particular curve. Let's say you want it to pass over itself, have 2 loops, one of which is much smaller than the other. Then perhaps you turn to this page, you see this loop, and this loop also, and you see all of these are coming close to that type of path that you're looking for. And so you know you can create such a path using a linkage of these ratios shown here, and by including the point. For example, if you decide to use this particular path, you'd simply draw a triangular shaped coupler whose point ends right there and goes back up. And so you'd have that path traced out as your crank went around 360 degrees. Here's an example of such a path. We're actually taking the one next to it in this case, the one shown here in gray. You see our linkage as was drawn previously. We have our crank, our coupler, our rocker, and our ground length. We've made our coupler into a triangle, including in it this point, and now we're ready to trace out this path that is shown here that has one chronoid right there. A couple of other things that are mentioned on this particular linkage is an angle phi, which is used to specify a vector r, which goes from the point where the crank and the coupler meet to the coupler point of concern. And so along with these ratios, you can then decide which actual coupler path you're going to pick up by specifying phi and r. Here's an example of a mechanism which could be the result of thinking about the coupler curve needed or the type of path needed. This is a film mechanism that would be inside of a projector to pull film down. You may recall film like a 35 millimeter film that has little notches on each side of the film running along it. And so what you have in this particular case is an arm that comes up and grabs the film. You see at C, you have a little point there that goes into one of those little holes on the side of the film and then pulls that film down. And then at this point where we have a cusp, it pulls back out of the film. At this point, the light is shining through the film onto the screen, and the arm comes back around to grab the next sprocket or the next little opening on the film and to pull it down again. And so we have this type of shape that we were needing for this mechanism, and then we went to an atlas and we perhaps found this particular mechanism. And as we see in this particular case, our coupler point C is basically right in line with the original coupler length. And so if we look back, here, what we'd find is that our phi angle is probably close to 0, because really we're out along the coupler, and our R is probably twice as long as our coupler length. And we can just show what this mechanism looks like here. Just show a quick video of how this mechanism moves. And so you see there that it kind of comes down straight using the guise of the film, and then pulls out and then goes back up to grab the film again. And so this is a great example of how a coupler curve can be used to design a mechanism to give us a particular purpose. Symmetrical 4-bar coupler curves. If the coupler and the rocker have the same pin-to-pin length, all coupler points that lie on a circle centered on the coupler-rocker joint with radius equal to the coupler length will generate a symmetric coupler curve. These are called the symmetrical 4-bar linkages. Again, just to restate, these linkages look pretty much like the ones we just saw, except for these facts. The coupler and rocker must have the same pin-to-pin length. So we're saying there that L2 must be equal to L4. All coupler points that lie on a circle that's centered on the coupler rocker joint, this is a joint usually labeled B, and have radius equal to the coupler length or equal to L3 will generate symmetric coupler curves. So let's take a look at this linkage. So here we have such a linkage where our coupler and our rocker have the same length. That was our first requirement. The coupler and the rocker have the same pin-to-pin length. Then all points that lie, all coupler points, and here's a coupler point that lie where on a circle that's centered on the point B where the coupler and rocker meet. That circle has radius equal to the coupler length. Okay, so let's go back. All coupler points that lie in a circle centered on the coupler rocker joint with radius equal to the coupler length. Okay, so this point here, this coupler point, is centered on a circle, and that circle is centered at the coupler rocker joint, and the radius of that circle is equal to the coupler length, L3. Okay, notice this coupler length is going from the center right over to here, which is on the circle, so that radius of the circle is equal to the coupler length. Every point on this circle will trace out a coupler path that is symmetric about a line that connects that point P, the coupler point P, to the ground position O4. And so here we have that axis of symmetry going from O4 up to the coupler point. The coupler point does indeed lie on this circle, which is centered at the coupler rocker joint and has radius equal to the coupler length. That point in this particular example will trace out this almost kidney bean shaped curve. And notice that this line here of axis of symmetry will cut this kidney bean in half such that this section and this section are symmetrical. They're exactly the same. They're mirror images of each other. So we could trace out a different path. For example, if we took this coupler curve, this coupler, and instead of having the triangle end here, we instead had the triangle go here, maybe to this point and come back down. We may not trace out a kidney bean, but we trace out some kind of path which would be symmetrical about a line coming right here. Here, up at the top, we show a couple of extra equations. We show an equation where we have a value delta, which is equal to 180 minus gamma over 2. And this is just a figure that helps us find particular curves in the back of your text. And we also have AP, or the distance from A to the coupler point, is equal to 2 times the distance AB, which is equal to L3, or the coupler length, times the cosine of that angle delta. To end up with such a symmetrical coupler curve, what we need to do is make sure that our crank is extended collinear with our ground length. Okay, so that's what we'll do first. So if you want to come up with a linkage that traces out symmetric coupler curves, the first thing you will do is make sure that a few things happen. Your coupler must be equal to your rocker length. There must be a circle that will have as its center point B, which is where the coupler and rocker meet. Its radius has to be equal to the coupler length. And then what you do is you extend your crank so that it is collinear with your ground link. And then wherever you put your point P on this curve and then connect it to 04, you will find a symmetric path generated at that location. These are this is a figure which shows a number of coupler curves that can be generated using our previous example. And these are all symmetric coupler curves, and they are created using the following numbers. For example, the ground link ratio here, L1 over L2, is given the following properties. So, for example, let's say that the length of the ground divided by the length of the crank is equal to 2. Then we are on this row. So right away we know, for example, if our crank has a length of 1 inch, that means our ground length will be 4 inches. And so right away we're on this particular row. On this row, for example, if we want to trace out something that looks kind of like a banana, we need to have a coupler angle gamma equal to 72. So if 2 is our ground link ratio and our coupler angle gamma is equal to 72 degrees, we'll have a class 1 mechanism, which is Grashof, and our coupler point will trace out this path. We'll also find that our other link ratios are as follows: L3 over the crank, L4 over the crank, and BP over the crank are all equal to 2.5. Now in this particular example, we said that our crank was going to have a length of 2 inches. If that crank has a length of 2 inches, then that means our coupler will have a length of 2.5 times 2, or 5 inches, will be the same as our that coupler will be the same as our rocker, which will also be the same as BP. Let's go back and take a look. BP is that length that goes from where the coupler and rocker meet all the way out to our coupler point P. And so right here we're seeing that we can pick out any type of curve that we want, and we'll immediately know how to generate it. We'll know how long to make our ground length, L1, and we'll know how long to make our other lengths and what to make our angle gamma, simply by choosing, in this case, our independent variable being our crank length, L2. Notice here that we can create class 3 mechanisms and class 2 mechanisms. Class 3 mechanisms are also Grashof, but they have change points twice per revolution. And class 2 mechanisms are not Grashof. And so you see here that these coupler curves do not come back and connect like all the others do, because there's a certain point where we have to stop and move our crank in the opposite direction because they are not Grashof. The axis of symmetry again is 0204. When the crank and ground are collinear extended, as previously shown, we need 5 parameters to define a non-symmetrical 4-bar linkage. Okay, so if we're talking about a 4-bar linkage that's non-symmetrical, we need 3 link lengths and the length and angle to the coupler point. So again, we need an L2, an L3, and an L4, and we need the length and angle to our coupler point in that case. And normally our L2 will be specified for us, and then after that we'll have an L3, an L4, and an L1 based on our H&N atlas. And again, we need the length, which is normally given by R, and an angle to our coupler point, which was given by phi. However, if we are doing a symmetrical coupler curve, generating a linkage for that, in that case we only need 3 parameters, 2 link lengths, and an angle. And we just saw that on our previous chart. Our next figure shows various symmetric curves. The difference in this particular table and the one previous is that in this case we instead look at not just L1 over L2 on the y-axis, but we look at L3 over L2, which is the same as L4 over L2 and BP over L2. We pick that number first, and again on the x-axis our angle gamma, and after we've done that, we find that L1 over L2 is always going to be equal to 2 for the entire chart. And so it's kind of a difference here in that before we chose this ratio on the y-axis and then found that this ratio, these 3 ratios were equal to 2.5. In this case, it's the reverse. We also have geared 5-bar coupler curves. This is obviously a more complex mechanism than a traditional 4-bar. In your appendix E, we show some additional curves. We have 8 independent parameters in that case. We have an additional link ratio, a gear ratio, and a phase angle when we're dealing with a geared 5-bar coupler curve. And here's just an example from the H&N, from the, let me see, oh, this is a different atlas. This is a Zane Norton Hammond atlas of geared 5 bars, and we can kind of see that the shapes or the paths that the geared 5 bars are generating are more complicated than those generated by the traditional 4-bar. And that's the end of our discussion on coupler curves.